I want to go ahead and try to, because I mean, what can we do next? So I think in order to understand this better, we gotta just get our hands dirty with this. So I wanted to. This is Guillaume's paper on approximating. This is the one that basically has the part where you approximate Grover with QA with CVQAOA, and this other paper is the one that they um, reference in the other paper. Um, it's kind of confusing today because here it says June 2000 and here it says October 2018. Anyway, and this is the one that actually explains the sort of an algorithm or sort of the Grover's, but not like a continuous version of Grover's, but not like approximating it from QAOA. So, and I think it can be an interesting exercise for my ultimate goal, which is to understand Grover's algorithm better and intuitively, sort of kind of improve my intuition around Grover's algorithm. Um, to take a look at both things, right? So first is just the approximation, via QAOA, and then there's the this other one here. Yesterday I was tweeting about it, and actually Guillaume himself answered with something might might kind of be interesting as well. This is this. If you start with a really wide Gaussian in position and a cost function which is the negative uh, the negative of a thin Gaussian centered at the point to be found, and I think that's basically the equivalent of the digital version basically putting the phase into negative, like negative, like in like -1. That's what the oracle does. You will see the Gaussian progressively concentrate uh, over the different iterations. Yeah. So that's what I want to try intuitively based on what is written in here, which is a bit, um, which is crazy compact, and it might take a while. So get ready for a long video, um, or even a couple of videos. I don't know if I'll make. I think I'll just focus on the approximation first, and then we'll go through these. Because here you've got like Fourier transforms and a couple of other stuff that might actually be helpful as well. But let's first try to understand. I don't know if this is gonna bring me anything, but I think it's good exercise regardless. So first I gotta find where the Grover part was here. But I don't know if here I have enough that I can understand. So first we show that QAOA circuits can encode Grover's search algorithm over continuous spaces, which is known to achieve a quadratic speedup. Oh, that's okay. So here, suppose that we have a target value. That's the one. Let's say, I don't know. Let's say, and we're gonna do this with the interactive. So let's say we wanna target, I don't know, something like 3 or something like this. Yeah. Maybe, yeah, 3. Where was I? Here. Um, I mean, let's make it. I don't know if we can make it even real, 3.5, but let's just say 3, with corresponding oracle function. Okay, so this is I think what he means by what Guillaume means by a negative. So a cost function which is a negative of a thin Gaussian centered at the point to be found, because I should put that aside. Exactly. Mm, 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 mm. Because this means, so if the xf is 3, right, then I'm gonna ignore this. I don't know if there's a constant or, but, but intuitively that would mean that at x3, then that's kind of 0. Yeah. Yeah, exactly. And then and then basically at x4 is 1, at x5 is 2, right? So it then kind of grows uh, and x2 is and -1, okay. Mm. This function can be mapped to a cost simultaneously by defining the indicator display. Okay, so maybe here there's a bit of intuition for us how to build that function, because that's what we want to do. We want to start with a wide Gaussian. I don't know how to do that, so I'm really just guessing around this right now. So I'm gonna, just in case, stay with the Fox simulator, because I assume that it's basically the one that allows us to simulate all the operations. Just in case, although I might have just what was my mouse here? Maybe Gaussian will be enough. I don't know. Um, and then I want to use. How can I add more? How can I add more modes? I want to add settings, because I want to basically use each mode to kind of then replicate the same that Jack did in his in his blog post. I'm going to use each mode to replicate, like one step, with 2 steps, with 3 steps, with 4 steps. So then I'm gonna get like different the different visual representations for each one of them, which I can then pack into a nice GIF. So and the age value. You've got a bunch of algorithms. I didn't know that. Interesting. User created. Gates. What is this? Oh, dark mode. Okay, cool. I don't know what I like the most. Let's stick with this, with a light mode. It's function be mapped to a cost simultaneously by defining the indicator displaced squeezed state. So we need a displaced squeezed. But that's for the cost function. Yeah. That's for the cost function. Because we need it displaced, and we need it displaced towards the value we want to find, and we need it squeezed because you want that negativity, if you want to call it this way. I don't know how to call it. You want that to be okay, or you want. I'm missing words. That's crazy. I'm missing the because with the digital quantum computing, you can still talk about negativity and the phase and stuff. But what is this? Is that like? I'm missing the language of this. And then as for the mixer, we choose a projector onto a state that is sharp in the momentum basis. Okay, minus, and it's this thing in here. Squeezed state. I'm assuming this is something, we're looking for something that because if I place in here, let's say I place a displacement, and I wanna, I don't know, let's say I have no idea what I'm doing. I really have no idea what I'm doing. Let's see what happens if I do this. We're totally jumping into, so we want to see, not, we want to see the quadratures of mode 0. What have we got? Oh my god, that's not what we want. That's definitely not what we want. What if the 3 is here? And I'll just say go. That's a displacement. It's not. What if I put a 3 3? Huh. Mm, Cartesian. So it can be entered in Cartesian form or in polar form. Okay. So what does it look like? I'm just playing with this right now. Help. Oh, that's why exactly. Displacement. So displacement. Mm, 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 mm. Displacement does whatever it is. The position of momentum operators. Mm, that's gonna be. That's gonna be a tough one to do intuitively. I want to do it intuitively. I really want to do it intuitively. So suppose that we have a target value. So the initial state will. I'll take care of this later. First, I want to try to understand what is the. So how to build that cost function, which I imagine should look somewhat like this. I guess. I think so. That's what I imagine this should look like. Around the 3, right? So here would be 3. But I may be totally wrong. And setting HC. The exponential of this cost Hamiltonian can be done. The exponential with this cost of this cost Hamiltonian can be done with quantum state exponentiation. 51, 53. So quantum state exponentiation. Ooh. Vectors, observables, multiple measurements. explanation. Those are really squares. Yeah, this is those are weird references. Difficult to find, I guess. Citations. Oh. And this one. I don't know. Physical review A98. A quantum approximate for continuous problems. Isn't that the same paper? I'm kidding. I mean, yeah, it is, but that's weird. Yeah, it appears because it references that. Quantum set exponentiation. Here, there's something. Doesn't approach for quantum Hebbian learning through a batched version of quantum state exponentiation. Here, batches of quantum data are interactive with learning and processing quantum bits, qubits by a series of elementary controlled gates. Exponentiation, processing qubits. Well, that is going to be tough. What the? So, Grover. So I need to build that somehow. Can do this by trial and error, but as for the mixer, we choose a projector onto a state that is sharp in the momentum basis. Namely, okay, so here we've got the Fourier transform for the mixer. Okay. That's a product of Fourier transforms on all modes, and x0 is some choice of initial momentum value. The resulting QI unitary is, this. Reproduces Grover's algorithm and it's speed up by setting the angles to pi. Okay, so there's still gonna be, still needs to be something like pi in here. Trial and error. Yeah. There is already some pi in here. That might be. What about we put? Let's see what happens if we put. So I want to have. I'm just gonna be playing with the different modes. I'm gonna have different things in here. So I'm really gonna try to do this by trial and error. That's probably nuts, but first let's just keep that 0 and see what happens if we keep 0, if we keep like a 1, if we keep like a 2, if we put a 2, if we set it to 3. So go. So what have we got? We've got these. We've got these, and these. 003, 004, 035. So you're basically, it seems like so the position, you're displacing the position, and there's a bit of stuff that's left in here. You're displacing the position as you increase that. Still, probably if you want to have like a 6 or something like that, that's where you want to. Oh no, that just increases the, okay, that doesn't, I want to displace it, I want to kind of displace it to 3, and then I want to negate that somehow. That's what I was trying to do. Okay, but then it must be a combination of, so if let's say I stay with 3, right? And now I only touch this other part. Let's say 0, 1, 2, 3. See what happens. Oh, sorry. 3, 0, 3, 1. Okay, 3, 2, 3, 3. I just wanted to keep. So what have we got now? This, this. Okay. Seems like it's kind of like there's like a bit of a cycle here, or I don't know, because here now the both position and momentum, they are kind of looking pretty similar. See, I just want to displace the. So what if I do minus 1, -2, -3, this. Seems like that second parameter is actually affecting the momentum. Oh. Okay, but I'm stupid because that should be 0 to 2 pi. That should be the angle. I feel so stupid, but I mean, the matrix elements of the displacement operator in the Fock basis were derived by Cahill and Glauber. Squeezing. Position and momentum operators like. Okay, so the imaginary. Okay, so maybe this is actually. So it seems so the real part is for the position, and the imaginary part is for the momentum. Okay. So maybe let's do it this way. So let's go back to this setup. I don't know, let's just stick with position right now. I don't really care what happens in momentum then. So if I just say I want to displace 0, 1, 2, 3, go. 0, 1, 2, 3. It's funny because it seems almost like the same kind of result we were getting before. But I can manage to displace it farther than that. Why is that? Because that adds to the position, right? Oh, so maybe it has to be that adds to the position. So okay, but the what if I set the Planck constant to be 1? Does this make any difference? 1, 2, 3. Yeah, it does. Okay. It does because it's part of these, right? So if I set it to 2, then 0, 1, 2. Okay, so now we got something that is okay. I like this. That's mode 2, and mode 3. Mode 2 seems like a good thing. Mode 2, and it's pretty. Could probably try to squeeze it a bit more. So basically, okay, so that's. Does it matter what I have on the momentum? Does this matter at all? If we just stick to one quadrature, it shouldn't. How does this change if I say minus? Why was it now this at? Oh my god. So clear all. I'm gonna put one displacement. I'm gonna put it in terms of tool, and I wanna run this again now. Quadratures. So I get what I want. And now, just out of curiosity, if I do something like -2, what does this do to the... Okay, yeah, that does this. So it seems like we can't really... I could move both, but I don't know if that would give me any... That messes up. No, let's not move it. Let's keep it like this as a displacement. But I would need to negate that if I understand this. Start really wide Gaussian, so the starting point is a different thing, and then okay, centered at the point to be found by Grover's search. You will see cross section is the negative of a thin Gaussian centered at the point. I want to squeeze it now, so I want to squeeze it a little bit. Squeeze. Squeezing factor. How does the squeezing factor look like? Squeezing factor. Squeeze gate of exposition and momentum operators as this. Radius. Squeeze gate affects the position of momentum operators. Okay. as following. But I'm trying to think about the whether it makes sense more in a Cartesian or squeezing parameter. What if I just say 3? Because now I got these, which basically spans from like 1.5 until like 5 or something like that. If I do that, then y this 3. So 3. Should I first squeeze and then displace? 4, 5, 6. Nothing changes. Nothing changes unless I then do maybe here something. Oh, now the opposite has happened. And so if we do it this way, what that does mean that basically we're squeezing here the position, right? I would assume. But I can't seem to be able to squeeze this more. If that's really what squeezing means in this sense, in this case. What is this? This is the fancy Wigner function. What the hell is this? Yes, it's kind of squeezed. Indeed. That's really not going anywhere. I think so far. So if you squeeze first, let me squeeze first and see what happens. If I squeeze first, you get something like this. And if you now displace, you get something like this. Okay. Pretty messy though. Displays kind of around 3.2 whatever. Squeezing. So if I how can this be negated though? This is what I don't understand. Then there's the mixer, which is the Fock. What am I saying? The Fourier transform. But I'm still. So we need to, this one thing. We need to start. So let me put this here. Really wide Gaussian. That's what we need. That's the starting point. That's what I wanna. How can I? Oh, displaced and squeezed. Okay, you can kind of start with displaced and squeezed. Stay squeezed, coherent, thermal, initial state. Okay, interesting. How can you start with a So we have momentum displacement. Displacement, quadratic phase, rotation, cubic phase, care, Fourier transform, position displacement. Maybe that's what I should use instead of the displacement. So I should use this. So what if I say now 3? Go. Now we got this at roughly 3. Messes up with the position, with the potential. Okay, so it displaces the position. So it's a better way to start with, probably. And can I squeeze it afterwards? So if I do this, I get rid of this. It's again, it's the if I squeeze after displacement, it's messing up. So if I squeeze first and displace afterwards, that looks better. That looks way better. Okay, I'm happy with that. That looks way better. I told you that was going to be a long video, so you squeeze, displace the position, but still if I negate that, it just goes on the other side, right? Yeah. But maybe that's what we need. I don't know. I don't know what Guillaume means by negative of a thin Gaussian centered at the point to be found. Is it negative as in like it should be... No, because the point to be found is 3, right? So that's definitely not. But you still want a negative, so how do you do that? Maybe with a phase or something like this. Displacement, care, rotation, momentum displacement, quadratic phase, rotation. What does the phase, quadratic phase do? So if I now do this, I have a parameter. This parameter is quadratic phase gate S parameter. I don't know. 3, 5. I don't know. Guessing. What's gonna happen now? No, that just phases the... I think that just phases position momentum. Then maybe a rotation. Let's see. It's a phase rotation. Phase-based rotation. So nothing happened. If I add 2, nothing happens. If I add like 10, nothing happens. Interesting. I can see different things in here. That's interesting. Fock states. So that's the... okay. 3. Aha, that's like... that's actually like states, okay. Like, that's actually like, you know, cats, I would say. But I don't know if negative means that I need to take this down, or negative is that You know what I mean? Uh, that's what I'm not. So map to a customer to define indicator displaced squeezed state. It's definitely displaced squeezed state. Hmm. Setting the cost of this. Okay. The exponential of this cost Hamiltonian can be done with quantum state exponentiation. Squeezing. This is position displacement. What if I do, I don't know, can you do something like this? What is the difference? I'm just gonna get rid of this for now. Yeah. Can you have a complex number in here? No. So there must be another gate that takes you if possible. I mean, because what's the negative of a function otherwise? So that's what he says. So the negative of a thin Gaussian. So what is the? I mean, that's just the negative of a function, right? So exactly below the Gaussian function. Does this make any sense? Gaussian functions are these things here. Wikipedia. And negative. The two dimensions. Okay, so in two dimensions, the power to which e is raised in the Gaussian function is any negative definite quadratic form. Consequently, the level sets of the Gaussian will always be ellipses. Okay, yeah. Yeah, but then there's no sense in this Gaussian in this taking sort of a negative form as I or is this just or is this just naming negative of a thing Gaussian? Start with a really wide Gaussian imposition. So this is the okay. So at least let's try to get the starting the starting state. A really wide Gaussian. How do you start with really wide? So this I'm gonna keep here. How do you start with a really wide Gaussian? Squeezing Fourier care. Position displacement, cubic phase, momentum. Maybe with negative squeezing. Can you do negative squeezing? Say -4. Because if I don't do this, if I don't do anything, this is what you've got. So you want a wide Gaussian. So how do you do that? How do you do that? Maybe with a Fourier transform. No. Why? Why would you? Displacement, no. Position displacement, momentum displacement, quadratic phase, rotation, cubic phase, shift, care, Fourier, squeezing, displacement. I don't want to squeeze it, I want to smash it. gonna smash it. So um, what about? Because I tried minus already. -2 squeezing factor. That squeezes it more. If we do something like that. I mean, now it's fairly wide, but it's not what we want. 2, 2. What does this do? This way, okay. Squeezing factor. So here we leave it at 0. Here we just say -2. What's going on with this? It's still. So how do I parameterize it so I get a wide a wide Gaussian? I mean, they're just kind of flat and wide, I would say. If I squeeze momentum, then I'm creating uncertainty with position. So that's what I want. So if this stays like that, and then this, and I do something like this, exactly. What if I do 4? Okay. 7. So the more I squeeze momentum, wait, now it's gone to position, being squeezed. Why? 5. Is it all the time? Ah, come on. 3. Okay, so this is still, and now 2. I don't know. Kind of 1.5. I mean, if I look at Fock states, quadratures for mode 0, I don't like that. Because ideally you want a superposition, right? What is the cutoff dimension? I guess it's adding. Interesting. It's adding the possible. Okay, so that's basically the where this thing stops here at +4, -4 and stuff like that. Okay. But ideally, I would like to have here some probability as well. I wanna have something that rather looks like this. So, but it's extremely tough to do that by trial and error. Okay, so I haven't really moved much forward, but basically that will be my first attempt to prepare like the initial state. You will compose these things later, right? Because here what I'm trying to do is I'm trying to make a the cos Hamiltonian, which is supposed to be the negative, a negative of a thin Gaussian centered at the point to be found, and this is intuitively what Grover is doing also in the oh yeah, but that's extremely how is the, I don't know, I still don't know how is that gonna help me understand Grover anyway, but it's definitely an interesting exercise. Gotta keep going with this. Yeah, I guess there's gonna be quite some more videos on that. um, if I come up with a couple of other ideas, then I'll definitely try to, you know, put everything in videos. Because that's gonna keep me busy for a while. But basically, because then I assume you do something like this, and then you would basically, you know, then the next one will be like what happens if I do a Fourier transform in here? Just out of curiosity, can I copy those things? No, that's the no, that's the inverse. What I just did. So if I do this, what happens in Q mode 2 and Q mode 1? It seems like it flip the. What if I keep doing squeeze X F? That's what I imagine this could look like, right? Squeeze F X squeeze X F. So you would have kind of these. This is 6, this is 3. There's nothing. This is a 6. This is a 3. This is nothing. So you know you would kind of repeat those things, and then yeah, but it's still that's there's something still here off. That's like your cost function is a negative of a thing Gaussian center at the point to be found, and you'll see because you want to see how your position, because this is what your initial state in here, so that would be the initial state, and then you've got like the cost and the mixer. You want to see at the end that your position, so the green thing, is concentrating here, and it's really not doing so. Momentum does though. Momentum does though. Okay, yeah, but I gotta still play with this. But the components are these ones, right? So I'm trying to still figure out how can how can we really get that negativity that Guillaume talks about. Maybe this is just a way I don't know. I'm missing something here. I get it. I'm able to get it sort of squeezed. I'm able to get it sort of squeezed around 3. That's the number I want to find. Um, I'm I'm not super happy with this. I really want an initial state that's like a more like an actual Gaussian looking like a sort of like, you know, as I said, like this. But we'll get there. We'll get there eventually. Cool.